Hello and welcome to the demonstration of the release notes of release 2.6 of our finite element simulation software NACS. In the following few minutes I want to demonstrate you the new features and some bug fixes concerning the NACS core, and also demonstrate the new features in a small hands-on in the NACS graphical user interface. So NACS 2.6 is a feature release, and therefore I would like to start with new features in the NACS core. We have introduced model order reduction techniques in NACS. Model order reduction allows a significant speed up of harmonic or transient analysis. Model order reduction techniques can be applied to single physics or coupled physics. And in the following slides I want to show you more details on the model order reduction techniques or methods we currently have implemented. And this is on the one hand the modal superposition technique, and on the other side the Krylov reduction. I want to start with the modal superposition, and as the name already might show you, to use this kind of model order reduction technique you have to carry out at first a modal analysis, and then in the next step those mode shapes are the base for the reduced order model. We can apply this model order reduction technique to harmonic as well as to transient simulations. And currently we support the following physics: on the one hand the pure mechanics simulation and the coupled piezoelectric analysis. Then the next method is the Krylov subspace reduction technique, and here the only thing that is required is that you specify the number of Krylov vectors that you would like to take into account, and NACS will automatically compute the basis required for that reduced model technique. This technique can also be used for transient as well as for harmonic simulations, but as I already mentioned, the only thing that you have to specify is just the number of Krylov vectors. We can apply that kind of model order reduction to either mechanical simulations, magnetic simulations, or magnetomechanical coupled simulations. In the acoustic physics, we have added support to import flow velocity results from stationary CFD results. So if you have exported your flow velocity in the CGNS format, you can directly import it in NACS and use it, for example, for acoustics in flowing media, as it might be the case for ultrasound flow meter simulations. Concerning that imported flow velocity, it makes sense to check what can be found in that CFD result, and therefore we have added 2 or 4 new results, and this is the divergence or the gradient of the flow velocity that can be computed as NACS result, and then allows you to investigate the flow velocity that you have imported. In the mechanical domain, we have added some new results. The normal projection of the mechanical displacement, the mechanical velocity, the acceleration, and the mechanical stress onto the surface normal of a simulation domain. We have also added support for the displaced volume of a surface, and we can now compute the sound pressure level that would be generated by a vibration. If you assume that you have got a plane wave that will be launched into the acoustical domain, then you can already export the sound pressure at the boundary to the acoustic domain. In the harmonic analysis, we have added a new frequency sampling subtype. So previously we had the possibility to use linear frequency sampling, logarithmic frequency sampling, reverse logarithmic frequency sampling, and now we have added the possibility to just allow an arbitrary list of frequencies that the user can specify, and in the exact order of that list the simulation frequency will be computed. To the lower right side you can see a small visualization of the different sampling types. As you can see, equidistant sampling between a start and a stop frequency for the linear sampling type, a finer resolution of the frequencies in the lower frequency, for lower frequencies in the logarithmic frequency sampling type. In the reverse logarithmic sampling type, we have a higher frequency resolution for higher frequencies, and we have an arbitrary set of frequencies for the frequency list. Then I want to conclude the NACS core presentation with some bug fixes that we have introduced concerning non-conforming interfaces. Here we found out that the NACS factor that we have used by default, it was a factor of 100, might have led to too stiff simulation results because the two computational domains were too stiff at the interface. Now we changed that behavior and used the default value of 20 for the NACS factor. So maybe you should review your simulation results when you use that better feature in previous releases. Another thing also concerning non-conforming interfaces is that if you have used different approximation orders, as depicted here on the lower right side, it's a just single supported cantilever who on the top side consists of two small cantilevers that stick together at an interface, a common interface, and one of those cantilevers used approximation order 1, the other one approximation order 2. And here it might have occurred that some unphysical mode shapes might have been seen or spotted in the modal analysis that also occur in the harmonic analysis and of course also the transient analysis. We have fixed that, and now we are using a higher approximation order for both sides, and then we arrive at the simulation result that can be seen on the lower right side, and this of course matches reality perfectly. Okay, so this have been the news in the NACS core, and now I would like to demonstrate some of that features in the graphical user interface. As you can see here, I've already opened the graphical user interface of NACS 2.6, and I want to start with the demonstration of the model order reduction methods. So at first I would like to show you a very simple example. What we can see here is a 3D plate. That plate, we want to carry out a modal analysis at first, so that plate is fixed in all degrees of freedom at that side of the plate, and we simply compute some eigenfrequencies of that plate that we will need later on. Here you can see the output of the NACS simulation. For example, the eigenfrequencies are listed besides the participation factor and the modal masses. The next thing that we want to do with that plate is we want to carry out a transient analysis, and this is something that I've already prepared. Here we see the same plate again. Right now we've set up a transient analysis of that plate with a time step size of 0.5 milliseconds, and we want to compute 2000 time steps. The plate is still fixed on that side, and here is a small node depicted green right here where we want to apply a force in Z direction. That means orthogonal to the plate surface. We are using that spike function. If you don't know what that function is doing, just open the signal editor right here, and here you can see the time domain representation of that function. It's a simple spike, small Dirac impulse, and with that currently selected time discretization, that means that we have this is the frequency domain representation of that signal. Okay, so this is what we want to do, and then finally we have some results. We want to compute the displacement of that plate, and on a history node here on the other side of the plate, here's the excitation, there's the monitor point. We want to compute the history result for the mechanical displacement and compare that later on. Okay, so I think we can start the transient simulation right now. As long as that transient simulation is running, I will save that analysis with a different name. So this is Krylov because we want to use the Krylov model order reduction technique right now. So for each physics that supports model order reduction, you will find an item solution method and a combo box that shows you some entries depending on the chosen physics. Full system is that we compute the really full system. And here we have two different model order reduction techniques. The modal superposition, this is what we're going to show later on, and now the Krylov reduction. For the Krylov reduction, we have to specify the number of Krylov vectors, and 10 should be sufficient at that point. We just save it, and this is everything that you need to do at that point. So you just say save and start, and then the simulation is beginning, and you can see right here that a Krylov subspace is computed for the physics mechanic. It seems like it's a little faster than the full system computation. In the meantime, we save again our simulation with a different name. We call it right now modal superposition, since this is the next model order reduction technique that we want to use. And if we want to use the modal superposition, we again go to the transient analysis specification and choose the solution method modal superposition. For the modal superposition, we of course need a modal solution file. This is what we've been computing at the very beginning of that hands-on, and this is the result file of this modal analysis. We just choose it, and that's all that we need to do. If we do it this way, all modes that are contained in that modal result file are used as basis for the model order reduction, and here you can see that this modal superposition reduction is also running. Now I have prepared a small Python script that allows me to easily visualize the history point displacements for all three simulations. And we can see right here that all model order reduction techniques match the full simulation pretty well. This is the mechanical displacement, the X component, the Y component, and here the Z component. And for all of them, it looks pretty good. To just demonstrate that it doesn't have to be that way, we can do two things for the model superposition. There exists here a settings button, and that allows us to select certain modes. Therefore, here different criteria can be used. For example, the normed modal mass. Let's say here in Z direction, we are choosing all modal masses above a certain limit. Let's say in Z direction, threshold is 1 to the power of -3. And so here 6 modes are selected. We close that dialog just by clicking on that red X on the top right side and apply the setting and recompute this simulation. And we can also modify the previously used Krylov analysis. Here we maybe save it with a different name. Let's call it Krylov 2. Krylov 2 because here we specify that we want to use just 2 Krylov vectors. If we do that, we can still recompute that result. It takes a few seconds, and then we can try to compare the result files again at that monitor point. And this is what we are doing right now. Comparison is running, and now we can see that there are certain differences found. here for the three components, we can see that for the model order reduction with the modal superposition, we see large differences since we just used 6 modes, and those 6 modes are maybe not well suited to represent that dynamic behavior of the system. We can see that the Krylov reduction with just 2 vectors still fits pretty well, but there are already differences that can be seen at the results. So this is everything that I wanted to demonstrate concerning the model order reduction techniques. Now one last thing. Here we again load our mesh file and set up a certain material for that plate. What I want to show as last item is here the change in the harmonic analysis setup. Here we have different frequency sampling types, and then new sampling type is called frequency list. Then another item here opens, and here we can either add just single items and enter a certain discrete frequency where we want to obtain results later on, or we can also open a frequency range definition, and let's say here we are interested in frequencies between 250 and 750 hertz, maybe 10 frequencies, and with that with a logarithmic sampling, so that means denser to lower frequencies. This is just added here. We can here change the order of certain items, or maybe also of several items, by using those icons right here. And we can also sort the list again. The computation later on is carried out in that order that is depicted right here. So we just add that. So this is everything that I wanted to demonstrate concerning the new features, and so I want to end my presentation now. So after the presentation, I would like to lose some words concerning the privacy policy of Symmetris, as it is currently a very up-to-date topic. We have modified our privacy terms that can be easily reviewed on our website at www.symmetris.de/privacy. We take care of the privacy of our user data, and therefore we will not sell that data to any other third parties. And of course, we will only send you emails if you told us prior that we can do so. If you don't want to obtain any emails from us anymore, please just unsubscribe to our mailing list. If you've got any questions or you want to mention something, contact us please using the email address gdpr@symmetris.de. So finally, if you've got any other questions, you are looking for some information concerning Symmetris services or NACS, just contact our website at www.symmetris.de. Or if you've got questions concerning NACS, you want to buy NACS, contact us at sales@symmetris.de. And if there are any problems using NACS, just contact us at support@symmetris.de. So thanks for watching and goodbye.